Okay, so we're going to work on measuring in radians. So we've summarized the word problem here. We'll read through it together, and I always find it really helpful, especially with word problems, to just draw some visual, whether it's a graph or it's like a picture of the situation. It helps make things a little bit clearer. So we got Linda here, she's flying a kite, and the string is 40 meters in length. Wonderful. Angle of elevation. So that's a really specific definition, the angle of elevation. I don't know if you're familiar with it, but the angle of elevation is always measured against the horizontal. So I have a horizontal plane here, and the angle of elevation is just the angle with that horizontal. So that's your angle of elevation, okay? We know that if this is the kite, I'll do my best to draw a nice kite here. Ooh, that didn't turn out so well. Oh yeah, we'll make a little 3D. Oh wow, that turned out way better than I thought. Okay, we got our kite. It's 40 meters in length, so that's important for us. Angle of elevation is pi over 4. Okay, that doesn't mean a lot. We could always do like a conversion to degrees. Have you guys talked about how to convert to degrees? So it does have a bit of a reference. Yeah? What do you do to convert to degrees? What did they tell you to do?
You multiply, if you want degrees, if you want radians to degrees, you multiply by 180 over pi.
Yeah.
And if you want the reverse, you multiply it by pi over
180. Perfect. So let's do this just so it makes a little bit of sense to us. What's nice about this is the pi's disappear, and it's really 180 divided by 4. It's going to give us 4 and 20, 45 degrees. Okay, so we got 45 degrees here. It also really helps to know our special triangles. We can bring up the unit circle. Maybe we'll do that after, but let's actually work on conforming our special triangles. But actually, before I do any of that, I should really finish reading the question. It might have nothing to do with what we started here. The new angle of elevation is pi over 3. Okay, so wind blows. We get a new angle of elevation. Here's a quick question. Do we know if that angle put the kite higher or lower? Hard to tell from...
higher.
Is it higher, you think?
Yeah.
What makes you think it's higher?
Well, I have a unit circle
What's that? Sorry?
right now. I have a unit circle.
Ah, okay. Let's look at it this way. Let's do a little bit of comparison. Let's talk about... I'm going to use red here to represent this one. Pi over 3. I want to do a comparison here. Pi over 3 in reference to pi over 4. Just quickly looking at this, I got to pick one being greater than the other. How might I know which one's greater?
Whichever one has the lower denominator.
Yeah, that's right? Same idea as like if we had 100 here, right? 100 divided by 4 and divided by 3. We know that the numerator is the same. So really, how does division affect this? Well, the larger denominator gives us that smaller number, right? This is 33, so we know that this value is bigger. Therefore, we have a larger opening or a bigger angle of elevation. Good. Those little tricks can actually come in really handy with triangle stuff. Just realizing what side should be bigger than another can really help you check your answers, because sometimes you'll put angles in the wrong spaces. Okay, so we've kind of drawn this. Determine an exact expression for the horizontal distance of the kite. So I gotta make... Can I make dotted lines? Nah, it doesn't look like it. I'll use the color green. So I've made a right angle triangle. I'm going to make another right angle triangle here. Okay, so we have two right angle triangles. One of them, we've taken this horizontal distance from there, and it's got a new horizontal distance. So the idea being that we went from this distance to this distance. And the same with the height here, we went from this distance, the vertical height, to this distance, okay? So our horizontal distance is shrinking, so it's getting less, okay? And our vertical distance is getting larger. So we got some general ground rules. Okay, I know I'm going to have a higher distance for vertical, but a smaller horizontal distance here. And that's just because the radius is only so long, right? Just like we're moving around a circle. These radians, pi over 4 and pi over 3, they work out really nicely. They are in some special triangles that they expect us to sometimes memorize. Let's see if you have any of them thought up. Do you know any of the special triangles off of the top of your head?
I know 60 degrees on the bottom, 30 on the top. It had 45, 90.
Okay,
And then 30 on the bottom, 60 on the top.
I'm going to change something because of what you said, the way you said it. You said... Which one goes on the bottom?
I think it would be 60 on the bottom.
Before you said it was 30. Why was that?
No. I was just thinking because I know they're the same and they're interchangeable, but how I memorize them is with whatever angle's on the bottom.
Okay. So let's try to figure out, this is why I was talking about trying to figure out which one's larger. Let's try to figure out, triangle angles aren't technically interchangeable. What it is we can rotate triangles, right? I can draw this triangle this way, and then I can rotate it. Looks something like this. Okay. And that changes, technically that's still on the bottom. Let's give a better example here. There we go. Now what's on the bottom and top has changed a bit, right? It's usually visually pretty easy to spot what the 90-degree angle is going to be. So I'm going to go on the assumption that you're okay with that one. Wherever makes our perpendicular, we're good with. This is where it gets a bit trickier, okay? What I always found for memorizing is memorizing specific values. So we have the value of 1, 2, 3. Sometimes this triangle will be known as 1, 2, and 3. The question is just where do we put 1, 2, and 3? And it's not just 3. We actually use root 3 as a value. And the other triangle here is 1, 1, and 2. They're really simple numbers, and what we do is we'll convert to rationalize them. A lot of times these aren't technically rationalized. We work on rationalize them when we apply sine and cos. But first, let's work on just kind of applying it here. We'll go with this top triangle here. This one's actually a little simpler. This one's an isosceles triangle, and if it's isosceles, that we know that these two corners must be the 45s. Okay?
Yep.
Yeah. And I'll just say this is 1, 1, and by Pythagorean's theorem, this must be 2. Okay? Sorry, this should be root 2, right? 1 squared, 1 plus 1, yeah, root 2. There we go. The other one, I have a 1, 2, and 3. And root 3, actually. I'll tell you that 2 is the length of the hypotenuse here. But then it gets a little tricky here. I'm not sure if this is 1 or root 3, or this is 1 or root 3. What I want to do is a comparison between these two values again. 1 and root 3, which value is bigger? Hopefully you're able to tell that root 3 has to be a little bigger than 1. Not too much, but it's a bit bigger just because in order to get to 3, you have to have a number larger than 1 because square rooting or squaring 1 doesn't change that value. We got to get up from there. So root 3 is a little bigger. What I then do for my triangle is I have to find which mouth is larger. Okay, so just visually looking at it, I can tell you that this is a larger mouth than this one is. Just like this one is a larger mouth than this one, and this one is a larger mouth than this one. Sometimes that can be hard to figure out, but using these ideas, think of it like even like a crocodile's mouth opening or something like that. We got a crocodile's mouth. The larger the opening, the bigger the angle. Okay?
Yeah.
So when we do that, the bigger angle also means the further the distance is here. So I need to put the larger value. So this would be the 1 if I was doing some kind of comparison, and this would be the root 3. So in this case, I'll do some erasing here. This has to be root 3 because it's opposite of the, oops, I said that one wrong. This has to be the 1. This has to be root 3 because it's opposite of the larger opening, and this has to be 1 because it's opposite of the smaller opening. And then no matter how I rotate that triangle, bigger opening, therefore opposite side must be root 3. Smaller opening, opposite side must be 1. Hypotenuse is 2. Hypotenuse is 2. Same idea, root 3, 1. I can kind of just keep going around the circle as long as I know the relationship between 1, 2, and root 3, okay? Sometimes it's just easier to memorize them, which is fine. The second piece is making sure you know what they convert to. This one is actually pi over 4. We figured that out. But we could also figure out the other two here. One of them is pi over 6, and the other one is pi over 3. Just which one's the larger angle? Which one's the larger angle, pi over 6 or pi over 3?
Pi over 3.
Yeah, so pi over 3, well, larger angle is always opposite of the larger side. So I can kind of line it up like that every single time. That one's going to be a 1/6, so I'll move it out. That one's in a good spot. I know we're doing a little bit of overkill here, but it's the idea is being able to, no matter where we are, we can kind of, or how our triangle looks, we can make some type of relationship between this. So pi over 3, pi over 6. Okay, so we've kind of done some work with special triangles. We still got to get back to this. What we then want to do is we can recreate our unit circle. Okay, so I'll kind of move up from there. Our unit circle here is just kind of like that video they were showing. We were looking at earlier. Do I have a shape drawing tool? I don't think I do. Okay, I'm gonna try to freehand this. Do my best. Okay, so we got, oh, that's not the object I wanted. There we go. We've got a circle. I've drawn worse. Okay, we have our circle. A lot of times, the reason this is called the unit circle is because the radius, okay, is 1 unit in length. Yeah. Okay, so we have that here, 1 unit in length. Now we can use our special triangles because wherever we move our radius, let's say I move it here, it's about the halfway mark, right? I can make a triangle. And if that's the halfway mark, that means this is the unit of 1. This is an isosceles. Isosceles, we know, actually creates pi over 4 from what we did before. Okay, and we're always looking at this angle. We're not worried about that angle up there. We're always looking at the angle in reference to the x-axis when we're talking about the unit circle. So pi over 4, we have that value. But our only little problem is in the special triangle we drew over here, I'm going to redraw it really quickly. We actually use these values, root 2.
Yeah.
Here I have a radius of 1. So I've got a bit of a problem here, right? I need to figure out how to make this triangle similar, but to have only a radius of 1 instead. So what do we do? Well, if you remember, in grade 10, they kind of talk about this a little. You can use a scalar, I guess is the best term for it, is a value to multiply the one triangle by to get to the other. So in this case, we would actually divide because we're shrinking, or you can multiply by a fraction, however you like to look at it. And in this case, it's a bit simpler. I'm going to be dividing by root 2. Because root 2, divide root 2, that will give me 1. Does that kind of make sense?
Yeah.
Yeah, so if I went root 2 over root 2, there we go, I got my radius of 1. Okay, I need to do the same to my other 2 spots of the triangle here. Since they're the same, I'm just going to literally write 1 over root 2 and 1 over root 2. This is an acceptable value. They might ask you to rationalize it. To rationalize it, all that means is they don't want a radical value at the bottom. So I can write the exact same thing here. And instead of putting 1 over root 2, I can multiply by
root 2 over 2.
Yeah, perfect. We just do a little bit of multiplication and we get root 2 over 2. Okay, root 2 over 2. This distance is important here. So we've got that, and now we also have our radian measures, pi over 4, pi over 4. So we're recreating our own special triangles here, trying to use some basic trigonometry that we learned maybe in grade 10. The other triangle, same concept. We actually refer to it twice in this one. There's one angle that's a bit smaller, and there's another angle that's a bit bigger. And then depending on your quadrants, there's some changes in terms of positive and negative values, but these are the three major angles we're working with. You're either working with this angle here, I've kind of drawn over it. Oops. This one here, which is pi over 6. And then this angle here, which is pi over 3. A little crowded in there. We'll go get a better visual. Online, there's some really nice versions to look at. What's interesting about this coordinate now, okay, I'm going to go back before I move on to the next triangle. I can tell you this coordinate. This coordinate this is the x distance, right? And this is the y distance. Well, this is literally that triangle we were working with, so I could call it root 2 over 2. Root 2 over 2. That's the x value and the y value of that very specific coordinate. We got that information from here. I could have called it also 1 over root 2. Just, depends on how you prefer to look at the number. Okay, so we've got that coordinate now. We've made a small triangle with it. We got to do the same thing with our other special triangle. So our other special triangle, okay, we have our 90 degree. This is the smaller mouth. That's 1. This is the larger mouth, which is pi over 3. Pi over 6 is the smaller one. Opposite of that is root 3, which gives me a hypotenuse of 2. Same idea. Because this is the unit circle, my hypotenuse is 2 in this one. I use those values. You might have memorized the exact one. It's common to memorize it this way because you're just using the numbers 1 and 2 or 1, 2, and 3. I got to just find that similar triangle. Same concept as before. I need it to be 1. So here, we're going to divide by the value of 2 because 2 divided by 2 gives me 1. Our angles don't change. Nothing happens to the angles in this case because it's still a similar triangle. But now I get 1 over 2 and I get root 3 over 2 as values. Okay, so this is where it's important to understand bigger and smaller triangles, right? Because I'm actually using the same triangle reference. I'll draw it here. For both of these angles, I'm just rotating it. So then when I go to make these coordinates, we're just going to work in quadrant 1 right now. When I go to write these coordinates, I got to decide how my triangle's been rotated. So right now, if this is pi over 6, well, I got to go pi over 6. What's the horizontal distance and the vertical distance? Well, the horizontal distance would be the adjacent side to this. So what is adjacent to this? Well, that would be my x value, which is root 3 over 2. And my vertical distance, well, that's going to be my opposite side, which happens to be 1 over 2. Same concept here. We're just working with the other angle. With the other angle, what is my horizontal distance? Well, it's going to be actually opposite. So my x value is 3 over 2, root 3 over 2, I should say. And my vertical distance is 1 over 2. Sorry about how messy that is there. But what we're trying to do is we're just continuously referencing our special triangles to make this. So if we ever don't have the unit circle, we can recreate it. A bit of work, right? You could also always just look it up online. There's a lot of wonderful, much nicer images of this. But now that we got this info, let's go back. A lot of info here. Hopefully we start to see some relationships, right? I'm using a pi over 3, pi over 4. Oh, we know those values, okay? And in fact, I can just reference my unit circle to actually figure out this question. I'm going to redraw it so it's a little cleaner, and then we're a bit closer to the unit circle. But we have that kite problem there. Get the unit circle in this picture. And in our kite, well, that's not a good color. It's not very bright. There we go. In our kite problem, we have first kite, which is pi over 4. So the question is, what's the coordinate here? This is pi over 4. Well, we can go in reference, right? We go reference, we get root 2 over 2 and root 2 over 2, okay? X being the horizontal and y being the vertical. This is x and this is y. I won't overlay it just because it gets a little messier, but we're going to just draw it a little bit bigger here. This one became pi over 3. Well, what's the coordinate? Well, pi over 3's coordinate we have right here is root 3 over 2 and 1 over 2.
Yeah.
X being this distance, this is our x value, and y being the vertical distance, this is our y value. So now that we know these values and we've got a bit of a relationship, let's bring this to the forefront. What has happened in our picture is we have a movement of that kite. This is our horizontal, okay? The kite went from here and it moved up to here. So in other words, we had a certain x distance. We'll write it in. Our x distance was root 2 over 2.
Yeah.
And it's now at root 3 over 2. Okay, so that was the distance. The question is, how far did we go for our x distance? Okay, so you can make the argument to say the x distance, so the distance of x, or maybe the horizontal distance, you call it h sub d, whatever you want to call it there, is the first x coordinate, subtract the second x coordinate. Very simple math once we've like broken it all down. I mean, we had to memorize some unit circles and special triangles, but really just ends up being a subtraction question once we have our values. So x1 in this case, x1 was root 2 over 2. So we have root 2 over 2. And we're going to subtract root 3 over 2. When we get that, we get root, what happened there? There you go, root 2 minus root 3 over 2. It's some number. I use a calculator at this point, but this would represent the horizontal distance, or the distance of x. Same concept for this one. For our y values, our height, or our original height, was root 2 over 2 again. That's nice. We'll use blue, it's a little darker. So root 2 over 2. And our new height was actually a half. If we go take a look, right? It's got a little higher here. It's a half. So same idea. The y distance is equal to y1 subtract y2. Y1 was root 2 over 2. And subtract 1 over 2. And we get root 2 minus 1 over 2, which again is some value. You could argue that this is an expression for it. The distance of y is root 2 minus 1 over 2, and the distance of x, or the horizontal distance, is root 2 minus 3 over 2. This would be keeping it in a real number form instead of having to break it down and estimating, right? So we'll jump out here. Whoops, that's the opposite.
Would this be, wouldn't you have to multiply them all by 40?
Sorry, say it again. Multiply by
40.
Oh, you have a great point. I'm doing it in reference to a radius. I haven't actually referenced the actual value. Yes. This is all technically a radian move. You're 100% right. I was working in radians, but you're absolutely right. We did know the distance. Essentially, we should have wrote it like this. Thank you for catching that. I should have said that this is a radians. That's how far we've gone. This was on the assumption that I didn't know how far the radius is. But because I do know how far the radius is, like you said, root 2 minus 1 over 2 times 40. And this one would be root 2 minus root 3 over 2 times 40. And then whatever those values are, use a nice calculator to figure it out. Does it tell you what it is?
I haven't. I'll check.
Yeah. What's neat about working in radians is the fact that we don't actually have to know what the radius is. If we don't know what the radius is, we can figure out a rotation. Remember, just like that GIF we had seen where a radian is like the arc length compared to the radius. So this is 1 radius in movement. This is about 2 radians in movement. 3 is about here, right? This is our 3 radians, right? So at this point, I'm saying radians because I don't know what the radius is. Halfway around the circle is pi radians. And then could go all the way around to the end. That would be 2 pi radians. And as long as we know we can do all our calculations without knowing the radians. And as soon as we get the radius, absolutely, like you said, multiply by that and you've got an exact unit value in reference to your radians.